We're going to continue working with net ionic equations, and I'm going to take you through one example of how to solve a net ionic equation using some of the solubility things that you've already been practicing in class, looking up compounds on the solubility chart and then splitting the soluble compounds into ions, leaving the crystalline ones intact. That all has a bigger purpose, and we're going to look at that today. Just want to remind you a couple of things from double replacement reaction notes that you've already taken. Keep in mind that in every double replacement reaction, we tend to find that the cations and anions are switching partners. Sometimes that makes a new compound that's a precipitate. Sometimes that makes a new compound that is a gas or a salt that we look at with a neutralization reaction. More on that later, but to keep in mind that the cations and anions basically switch and that we use our solubility chart to try to look up more about that. So what we'll do is start with a balanced double replacement reaction equation, and you should have an example page that has four beginnings of double replacement reactions. The first one is the example that I want to go through with you first. So you'll notice on it that there are words to begin the equation, and then we're going to move on toward an actual balanced chemical equation. So with barium chlorate and potassium phosphate, you basically just want to come up with the new compounds by name first. And hopefully, with our practice that we've done already, you can take the cations and anions and switch partners, essentially. So barium will go with phosphate, and you can simply write that name. No Roman numerals required here, so pretty straightforward. And on the other side, potassium with chlorate makes our second product. So once we've got those down, we can write the balanced chemical equation. This is all just nomenclature practice, so I won't take a lot of time going through the nomenclature and how to write chemical formulas, because we've practiced this at great length, and you should be pretty comfortable with writing out compound equations, or formulas rather, for ionic compounds like these. So our reactants, barium chlorate and potassium phosphate. Our products, barium phosphate and potassium chlorate. Pretty straightforward. All right, and then what we'll do next is take a look at our solubility chart and decide who's who here as far as being soluble or not. Okay, so step one, we've got a chemical double replacement reaction equation. Oh, we ought to balance it, so let's quickly do that. I forgot to do that with you. We've got 3 bariums we need to get on the left, and that gives us 6 chlorate ions, 6 ClO3 ions. So to get 6 over here, we'll put a 6 in front, and then to balance our potassiums, we need a 2 in front of our potassium phosphate, and that should do it. Okay, so 3, 2, 1, 6, the way that I've got them written here. And as always, you can switch those products around in order, just as long as you keep them written correctly. We've got our double replacement reaction equation done. So the next step is to look up the reactants on the solubility chart and see if they're soluble. Label them as AQ if they are, because we're going to split them. And we'll do the same thing with products as well. So look up our reactants on the solubility chart. Well, here's that table. And if you remember, we've got barium chlorate and potassium phosphate. If we look those up, generally we'll find that in a double replacement reaction, both the reactants will be soluble. So here's barium chlorate, kind of right in here on our solubility chart, and I'll circle them for purposes of this. And then potassium phosphate, if we find potassium and go across to phosphate, it too is soluble. Pretty much every potassium compound is. So those are both soluble. So back in our equation, we can label those both as AQ because they are about to dissolve. At different times, we might label those as crystalline, but right now we'd be working with them in a bottle in a solution, and we'd be mixing them together to allow the ions to combine. So we'll label those as AQ, and then we want to look up the products in the same way. So we'll continue on looking at our products and labeling those too. If they're insoluble or soluble, give them the appropriate symbol that we've been working with up to this point. All right, so again, back to our solubility chart, and we'll look up barium phosphate. You should find that when you do this on a solubility table, they more or less make sort of a 4 corners of a square because you recombine the ions. So barium phosphate we'll find over here, and there's our insoluble compound. You notice a lot of phosphates are, and some bariums are, and that's our example. So that one's insoluble, while on the other corner, potassium chlorate is soluble. Again, as most potassium compounds and pretty much every chlorate compound would be. So the insoluble one is our phosphate, and so we'll label it that way with our CR, and that's a really important one to identify because that one's going to be treated a little differently as we've been practicing in class. All right, so we've got our equation, and we're ready to go on from there. We've got our balanced equation, we've looked up reactants, we've looked up products, and given them their labels. All right, the next step, what you want to do is take the compounds, the 3 that we have in this case that are aqueous or soluble, and split them. So we'll do what we've been doing in practice and split those into their ions the way that we normally would. So barium chlorate will switch, or split rather, into barium and chlorate ions. So we'll have barium, 2+ ions, aqueous. We'll have chlorate, -1 ions, aqueous. And we want to make sure to balance this as well. Now, in practice, we haven't usually had a coefficient in front of this, but because we do, you want to take that into account here. 3 barium chlorates will split into 3 bariums, so that's 3 here. And we'll get 3 times 2, 6 chlorates. Just when we were balancing the equation, there were 6 chlorates. Here we've got 6 as well. So 6 chlorates. And then potassium phosphate will split too, because it's aqueous. So this will split into potassiums, +1, aqueous, and phosphates, -3, aqueous. Excuse me. And again, we want to show the coefficients taking place here. We've got 2 potassium phosphates, so that means a total of 6 potassiums and 2 PO4s, right? So not 2 times 4, but 2 phosphates, and that would be a 2 in front of the whole thing, like so. So we've taken this first compound and more or less split it into 2 parts, and we've taken this second one and we split it into 2 parts as well. So it's kind of branching out that way. And then the arrow, right? And now the crystalline compound is our barium phosphate. That's going to be our precipitate in this compound, in this reaction. And so we want to treat that one as a crystalline, insoluble compound that won't split. So we'll leave that one intact and simply bring it down to the next line unchanged. That's really important. You don't want to change it because it's not going to dissolve. So we'll leave that one as crystalline, and it's going to look a little different. And then this one, potassium chlorate, like the first two, is soluble. It's an AQ, it's soluble from our solubility table, so we want to split it up. Potassium chlorate will split into potassiums with a +1 charge, and chlorates with a -1 charge. And you should find those charges are the same as they were on the other side. Okay? And again, because there's a 6 in front of that, we want to put 6 potassiums and 6 chlorates. So this big equation here is what we call a complete ionic equation. It shows every ion in the reaction and our precipitate, which is barium phosphate, that one that's not split, that we treat a little bit differently. Now this is a big, wide equation. That's why the page that I gave you in class is oriented the landscape way, so you have enough room to write. So feel free to spread out. Don't be so squashed that we can't have the details, and make sure you have charges and states on everything. All right, next step. We've kept that balanced, we've shown charges, we've shown states, so we've done a nice job with all that. And as I mentioned, the insoluble substance, our crystalline barium phosphate, in this example, stayed the same. All right, number 5. What we want to do next is find ions that are found identically on both sides. Those are called those spectators, and we've mentioned those a little bit in class. They're not doing anything. They're just starting out and ending in exactly the same state and fashion. So we're going to cancel them out because they're really not important players in our reaction equation. They're spectators. So go back to our equation. I'm going to switch colors just for the sake of making this pop a little bit. Let's switch this over to, let's see, maybe use a green for us. And, oops, pardon my delay here. All right, so we want to find ions that are the same on both sides. I have barium on the left as an ion. I have barium in a compound on the right. That's not the same, so we can't cancel that. But we have 6 chlorates on the left as a solution or in solution. And we have 6 chlorates on the right, ions in solution. So we can cancel those out. And a way to do that is neatly just to put a line through each one. Potassiums, we have 6 potassiums on the left-hand side, and we have 6 potassiums on the right-hand side. So we can cancel those out too. Those are exactly the same. It's kind of like playing concentration when you're a kid and finding matching pairs, which you probably beat your parents at or they let you win. That's the same kind of game we're playing here, but they have to be identical matches. And then lastly, we have 2 phosphate ions here on our left side, and on the other side, those phosphates are part of our precipitate, so we can't cancel them because they're not the same. Now you've canceled those out, and again, these chlorate and potassium in this case would be spectator ions. Spectators are those ions that are not affected or changed from one side of the reaction to the other. Spectator ions that we've canceled here and here. So those spectator ions don't play an important role in what we see in the reaction. They're there, they're behind the scenes, but they're sort of invisible to our eye. All right, last step. We canceled those out. And finally, we'll take everything that's left and rewrite it neatly as what we call our net ionic equation. Basically, what's left after the dust has settled. Okay? And what that'll do is show the ions that have taken part in the reaction and have formed the precipitate. So we'll have a really neat, tidy, short little reaction left by the end. So go back to this, and again I'm going to switch colors once more here just for, again, a little setting things off a little bit. Try to get this over to a blue for us. And for a net ionic equation, all you do is look for what's left. What didn't you cancel out? Well, I have 3 baryons. And I'll bring those down then. Be sure to bring their charge and their state. I have canceled out my chlorates and my potassium, so those are gone. But I have my phosphate here, so 2 phosphates. Those are left behind. And on the other side of the equation, my barium phosphate remains. So I have 1 unit of barium phosphate. And that's a precipitate, so watch that state, that's crystalline. And the other things have canceled out. So in the end, this is all that's left. It looks pretty neat and tidy, very small. In the end, what happened in this big, complicated double replacement reaction that we could see in a test tube or a well, in a well plate, simply going on there was barium ions and phosphate ions combining to make our precipitate. The potassiums and chlorates act behind the scenes, essentially. And that's it. You've got a balanced chemical equation with states. You've got a complete ionic equation that shows everything, states, charges, coefficients, and every ion that takes place working on its own. And then the net ionic equation, what's left, the net result of our reaction, which was barium and phosphate ions combining to make barium phosphate, our new precipitate. And that's a really important word maybe to keep in mind, precipitate, as the stuff that's made as a crystalline compound at the end of a reaction like this. And that's how we'll know it's there. It's insoluble in our chart, and it's got a crystalline state label here. That should be it. Why don't you give number 2 a try, and we'll take a look at that one next time we're together. Talk to you then.